Sorry, I gotta get started. All right, everyone, we're going to get started. So first, a few logistical notes. So homework 3 is out at this point, and I would really encourage all of you to get started on homework 3 early. So there's going to be a component on Q-learning, a component on ActorCritic. The Q-learning component will have you running your code on some Atari games, learning from images and so on, which is a lot of fun, but it also takes quite a while. So to make sure that you have time for all of your code, not only to get written and debugged, but also to actually run it, please do start on homework earlier. You know, if you have a computer with a nice GPU, it can finish in like a few hours. If you are running it on CPU, it might take as much as 12 hours. So do make sure to start early so you have time for your code to finish. And then remember, the project proposals are due next Wednesday. So instructions for project proposals have been posted on Piazza. They've been there for a little while now. Do make sure to read those carefully. We'd like to make sure that you address all the important points in your proposal so that we can give you good feedback, and also so that your peers can give you good feedback. And that feedback is important to make sure that your project topic really fits with the course, that it has sufficient scope, and so on. So do pay attention to the project proposal. It's really there primarily for your benefit, to make sure that you get feedback on your project before it's too late to change things. All right, so today's lecture. Today we're going to start our unit on model-based reinforcement learning. So up until now we've been discussing a lot the topic of model-free reinforcement learning, and we're going to change over a little bit to talk about model-based RL. But before we do that, today we're actually today is going to be kind of a no-learning day. There's not going to be any learning of anything. We're just going to talk about the control problem. How do you make decisions if you know how the world works? And then next week we'll bring back some learning and actually talk about how that can fit into the framework of a model-based reinforcement learning algorithm. So today we're going to introduce model-based reinforcement learning, but we're not actually going to do any learning. We're going to talk about what happens if you actually know the dynamics, if you know the transition functions, or you know the laws of physics in the world. How can you use that knowledge to help you make decisions? We're going to talk about some stochastic optimization methods. We're going to talk about some methods for search in discrete action spaces like Monte Carlo tree search, and then we'll have a discussion of continuous optimal control and trajectory optimization. So the goal for today's lecture will be to understand how we can perform planning with known dynamics models in discrete and continuous spaces. And then next week we'll say, well, okay, now if you don't know the model anymore, you want to learn the model, here's how you can learn it, and put it back together with the planning and control algorithms that we learned today. Okay, so by way of an introduction, let's go all the way back to the reinforcement learning objective that we covered at the beginning of the class. So if you remember, at the beginning of the class, I wrote out this reinforcement learning objective, which I defined as an expectation under a trajectory distribution. And the trajectory distribution is given by a big product over here of the initial state probabilities, the policy, and these transition probabilities. And in model-free reinforcement learning, which is what we've been covering so far, we assume that we don't know the transition probabilities. But not only that, not only do we assume that we don't know them, we're actually not even going to bother to attempt to learn them. So all the algorithms that we derived, they don't even try to figure out what these things are. They actually try to bypass it, generally with sampling, by generating samples from the world and not really needing to know what these probabilities are. So what if we actually knew those transition probabilities? What if we knew the dynamics, the laws of physics, whatever you want to call it, basically how the world works, how the current state in action transitions us to the next state? That's not a very unusual situation. There are actually very many problems where we do actually know the dynamics. For example, if you want to play a board game, if you want to play chess or Go, you know the rules of that game. It's governed by actually fairly simple rules that you can write down on a sheet of paper. You can implement them in a computer, so that's a setting where the dynamics are known. There are many physical systems that are actually pretty easy to model. So there are some very complex systems, like trying to build an accurate predictive model of the stock market is extremely difficult. But trying to build an accurate predictive model of the kinematics of a car is actually pretty straightforward. At some level of abstraction, just a little bit of trigonometry basically tells you what's going to happen. And then, of course, oftentimes we're working in just simulated environments. So if you really want to build a controller for a simulated system, presumably if it's simulated, you know how it works because someone had to write that simulator. And then in cases where we don't know the dynamics, oftentimes it's actually quite feasible to learn them. So, of course, in robotics, there's this entire body of work called system identification, which deals with identifying the unknown parameters of a physical linkage. You can use general purpose models like neural network models to fit the transitions from observation. So if you observe a bunch of transitions, you just can try to learn to predict the next transition, the next observation, given the current observation in action. So that's just a learning problem. So even if you don't know the dynamics, sometimes you can learn them. So does knowing the dynamics make things easier? And oftentimes it does. And oftentimes, actually, if you know the dynamics, you can control your system without needing to do any additional learning. It just boils down to an optimization problem that you can just implement and solve. So let's talk about this model-based reinforcement learning. So model-based reinforcement learning is when you learn the transition dynamics, and then you figure out how to choose actions using those learned transition dynamics. So there are a few general formulas. Oftentimes they involve iteratively updating your estimate of the transition dynamics, but the high-level idea is always the same, that you're going to try to learn the transition dynamics and then use those learned dynamics to choose actions, and sometimes you'll alternate these steps. Today we're going to talk about how you can make decisions if you already know the dynamics, if someone already did that learning for you. So we'll talk about how you can choose actions under perfect knowledge of the system dynamics. When I keep saying system dynamics, just to bring this back to graphical model land, what I mean is this edge in our graphical model. So this edge represents the probability of the next state given the previous state in action, and don't worry about the fact that I suddenly started using X's and U's. It's because I forgot to update my slide. But we'll actually see a lot of this notation later on because that notation is a little more common in optimal control, so we'll just use it for consistency with the optimal control literature. So if you see the term optimal control, trajectory optimization, planning, those are all referring to different methods for figuring out how to make decisions when you know the dynamics. And then next week we'll say, well, how can we learn the unknown dynamics? And then plug in these methods to use them to choose actions. And then afterwards, we'll also talk about how you can learn policies. So for now, a lot of this discussion will not really focus on policies or where they come from. It'll just focus on choosing the actions, but you can also do model-based RL to choose policies. Okay, so let's kind of write down some optimization problems that we might want to actually solve if we're to choose good actions. So before we have this view of reinforcement learning, you have some state or observation, you're going to be choosing some action, and your policy gives you a conditional distribution over actions. Now, we're not going to worry about policies for now. We'll just worry about what makes a good action or a bad action. So we can say, well, maybe in this tiger example, you want to minimize your log probability of being eaten by the tiger, conditioned on the sequence of actions that you choose. So we'll say you have a cost function or a negative reward function. So the cost here is log probability of being eaten by the tiger. And maybe you have some probability of being eaten by the tiger at every time step. You want to minimize that. And then you want to minimize it with respect to all time, so from 1 to capital T. And in the case of, let's say, deterministic dynamics, we can write this down as a constraint optimization problem. We can say you want to minimize your total cost with respect to your states and actions, but you have a constraint that says the next state has to be consistent with the previous state and action. So if you know that f of st comma at gives you st plus 1, then you impose that as a constraint. So this forces you to optimize over the states that are actually physically going to be reached. So in the case of deterministic dynamics, things can actually be fairly simple. So in the deterministic case, how can you model what's going on? Well, you have the environment, you have your agent. Your agent observes the first state. So the environment tells the agent, here's where you're at. You know, the tiger is 3 meters away from you, and so on. and then the agent thinks really hard, solves this optimization problem, and spits out a plan, A1 through A capital T, a course of action. And then the agent goes and executes that course of action, step by step. So that's what you get if you solve, sorry, this should be ST plus 1. This is what you get if you solve this optimization problem, right? So if you solve this optimization problem, that basically amounts to saying someone told me the first state, I'm going to produce my sequence of actions, and then go and execute them in the world. This is sometimes referred to as open loop control, and we'll learn about that term open loop in a second. You can also have a stochastic version of this. The stochastic version of this looks very similar, but of course, since everything is stochastic, we need to deal with expectations and we need to write down probability distributions. So now we're choosing a sequence of actions, so we're conditioning everything on those actions, and the distribution is over the only thing that's left, which is the states. So you have some initial state distribution, and presumably you know something about that, or you at least observe a sample from it, and then you have your transition distribution, which again here we're assuming is known. So that induces a conditional distribution over all of your states, condition on all of your actions. And you can write down the same optimization problem, well, the stochastic version of it, which is to say, well, let's just optimize our actions that'll maximize the expectation of the total reward conditioned on those actions. That's a well-defined optimization problem if you, let's say, have either discrete variables or you have some tractable class of continuous distributions. This is kind of, this is a very reasonable way to formulate the problem, but it's actually impossible to get optimal behaviors for some types of systems using this approach. So what I'm going to claim is that for some stochastic dynamics, solving this optimization problem will not give you the optimal actions, meaning the best actions, the ones that will actually maximize your reward. Can anybody guess why this might be the case? Or maybe give me an example of where this would not allow you to find the optimal behavior. Can you say a little more about that? Any other guesses? So, oh, yes?
There is a case that if you take action A, you're not going to land in a state that you expected. Like, you might go somewhere else. That you can take better actions from that state and go like
right.
The optimal.
So that's exactly the answer. So the answer was that, well, if you take action A1, let's say, and you land in a state S2, which is not the state you expected, maybe the action A2 that you had planned is not actually the best action to take from that state. So like an example for this might be that if I tell you, well, homework 4 is going to be either about model-based reinforcement learning or exploration. Now tell me which actions you will take to like implement the solution to homework 4. Well, you'll probably tell me, let me wait a little bit until you release the homework and I'll see what it's about and then I'll tell you which actions I'll take, right? So in a stochastic environment, each state you observe gives you some additional information that is not apparent from only observing the first state or knowing the dynamics. But in the deterministic case, of course, once you know the initial state and you know the dynamics, everything else is known. So it's a deterministic universe where everyone is sort of at the mercy of fate. Whereas here, there's random chance, and you might get things that you didn't expect. So it might make sense that you can get better reward if you're allowed to actually react to those observations. So in general, the stochastic open loop setting can be suboptimal. So what's the deal with all this loop stuff? Well, when we say that you're doing closed loop control, what we mean is that there's an environment. The environment is in some state ST. The agent observes that state or observes an observation of that state OT, and then takes an action according to some policy. And it's called a closed loop because I drew it like a circle and it's kind of like a loop. Open loop means that this back and forth relationship doesn't happen every time step. So open loop means that the agent still observes something. Maybe the agent observes the initial state or something about the problems. You know, what is it that the user wants the agent to do today, something like that. The agent emits a plan for many time steps and then simply commits to blindly following that plan. So that's the open loop setting. Yes?
Is this the same thing as off policy and on policy?
The question was, is this the same as on policy or off policy? Not really, no. So open loop and closed loop just refers to how does your controller work. It has nothing to do with how the controller is learned or acquired or optimized. So you can, for example, use a learning algorithm to learn an open loop controller, or you can use a learning algorithm to learn a closed loop controller. Yes?
To be clear, was the first equation narrowly optimal in the sense that it was optimal given the information it had? I can see.
Well, yeah, by definition, because it's a max.
Right.
Right. So when I say suboptimal, I mean if you do this, you will not produce optimal behavior, meaning that you will not maximize your reward as much as it can possibly be maximized in that environment. Okay, so in the open loop case, you just get something at the beginning, and then you commit to a plan, and it's kind of a one-way communication with the environment after that. So you could have the stochastic closed loop case, the one that can allow you to actually optimize truly optimal policies, but the stochastic closed loop case is quite a bit more complex because you can't simply commit to a fixed course of action. So in the stochastic closed loop case, you have to have a policy in there because that policy needs to be able to react to states. So the policy needs to depend on the latest information that is available. And then the problem of optimizing these closed loop policies looks exactly the same as the reinforcement learning objective. It's just maximizing the expectation of the total reward with respect to the policy. Of course, how you actually represent this policy is a choice, and the kind of reinforcement learning algorithms we covered so far provide one choice. So you could represent pi with a big neural net that maps from states to actions, which is kind of a global policy. It's a policy that that can choose a reasonable action, hopefully in all states. You could also have a much simpler class of policies that are not going to be global policies, but they're just meant to do something good locally. They're meant to respond intelligently to small random variations in the state. And we'll actually cover a stochastic closed loop control algorithm that makes no use of any sort of learning based on time-varying linear controllers at the end of today's lecture. So if you have a low-dimensional state, maybe your state is the position of your car on the road, you can get some basic control over it by writing down a linear controller that says, well, I'm going to react to my state by multiplying it by some number and then adding some constant. So maybe you optimize the plan is represented by these open loop terms, and then if your state deviates a little from where you expected, you'll apply some very simple linear feedback. That's a reasonable way to get, let's say, a local time-varying controller. It's sort of a generalization of a plan to the closed loop setting. So just keep in mind that when someone says closed loop, they don't necessarily mean that they're building a huge, powerful policy that knows what to do in every possible state. They might just be building a plan with a little bit of feedback locally to keep it from deviating too far from the states that were expected. All right, so more on this later. But for now, we'll start by talking about open loop planning because it's easy to get a handle on, and in many cases, open loop planning could actually be good enough. So open loop planning means that you observe where you are in the environment, you emit a plan of action, a sequence of actions, and then you blindly execute those actions. So how can we do open loop planning? Well, we have to solve this optimization problem. One of the simplest ways to solve this optimization problem is to just not worry about the fact that this is a sequential decision process and just treat it as any other optimization problem. So you can abstract away all of the sequential stuff and just say, well, okay, I have some sequence of actions. That sequence of actions needs to maximize some objective. It's total reward that I get if I actually evaluate the states I'll get from taking those actions. I don't really care what this objective is, so long as it's something that I can evaluate, at least approximately. So I'll just set up a generic optimization problem and search for a solution. So for notational convenience, since I'm kind of ignoring all the structure in the problem, I'll just call this capital A. Capital A is a sequence of actions, and I want to find the argmax of some objective with respect to capital A. Many different ways to solve this problem. You can use your favorite optimization method. You can plug this into gradient ascent, LBFGS, whatever. If you have a relatively low-dimensional action space and you want to plan over a short horizon, and maybe you're under some time crunch because you started homework 4 at the last minute, a very good algorithm for doing this that's very simple in very low dimensions. I wouldn't say very good. Okay, I shouldn't say very good. Very simple. very simple, is to just guess and check. Kind of not something that you really find in an optimization textbook because it's kind of silly and really, really simple, but it kind of works. So what you can do is, if let's say A is on the order of 10 dimensions and you need to plan over, let's say, 4 time steps, something pretty short, which is good enough for some simple control tasks, you can just sample n different sequences of actions from some distribution. Maybe it's a uniform distribution over all possible sequences of actions. Evaluate the objective for each of them, and then choose the action sequence based on the argmax of that objective. So this is, guess and check sounds kind of lame, so if you want to impress your friends at parties, you can call this the random shooting method. But it's really just guess and check. So I just wanted to mention this because, it works. Like it has also some advantages. You can parallelize it very easily, and for low dimensional problems or shorter horizons, it's a decent way to optimize your objective function. Now, if guess and check is a little too simplistic for you, you can actually build a much more powerful optimization algorithm that works a bit more consistently and will get you much closer to the optimum by improving on the guess and check method a little bit. So the improvement is something called cross-entropy method, or CEM. And the idea is very simple. The idea is that you're going to change this distribution from which you're going to sample your action sequences. So sampling your action sequences from the uniform distribution, basically from all possible action sequences, that's very unlikely to randomly get you the perfect action sequence, but it might get you a decent one. The higher your dimensionality is, the less likely you are to land at a good optimum just through random chance. So maybe you can boost the odds a little by changing the distribution to move more towards good action sequences. So can we do better than the uniform distribution? Well, the intuition is the following. Let's say that I sampled from the uniform distribution, and the height of these bars represents my objective value j of capital A. So now, if I were allowed to sample again, what I might say is that, well, there seems to be some good stuff over here. Maybe I should just sample more over here. So perhaps what I will do is, instead of sampling the second time again from the uniform distribution, I will adjust my distribution to put more mass where the good stuff is. And then I generate some more samples over there, and then it becomes even clearer that, oh, the good stuff is right there. So I fit a distribution that's even more peaky, and then repeat this a few times and hopefully zero in on the optimum. So, and by the way, when I say sampling here, now this doesn't really mean sampling in the environment like running a policy. It just means sampling action sequences and using my known model to evaluate their total reward. So the cross-entropy method with continuous valued inputs works like this. You first sample your actions from some P of A, and maybe initially P of A is just the uniform distribution, or maybe P of A is a very broad Gaussian distribution, some kind of initialization. Then you evaluate your objective value for each of those action sequences, just like with the guess and check method. And then you're going to pick the elites. So you're going to choose some number of A's, M A's, where M is less than N. 10% or 20% can work well if you just want a number to get started. You're going to pick those elites, and then you will refit your distribution to those elites. So maybe over here, we have 4 samples, which is a very low number of samples, but just for visualization, and the number of elites was 2, so we picked those 2 taller yellow bars and fitted our Gaussian to those. And then you repeat this process. So if you want to set this up, if you have a task with 10-dimensional action space, maybe you have 5 to 8 time steps, you can probably get away with a population size of 64 or 128 and maybe 16 to 32 elites, and you'll get something. So typically we would use a Gaussian distribution for P of A, which is very easy to fit. If the number of samples is or the number of elites is not very large, probably you want to use a Gaussian distribution with a diagonal covariance, because fitting a full covariance will not work if you don't have enough samples. But this method can work decently well. And if you have if the number of dimensions, meaning the number of action dimensions times the number of time steps, so the number of dimensions in the optimization problem, is on the order of 50 to 100, this method can work. If it's much more than that, then you're kind of in trouble. If it's less than 50, then you're in really good shape.
Question.
Yes?
What about it's a Gaussian mixture if it's like mean at -5, one mean is at 5? then it can, if you use just one Gaussian, it can change it.
Right, so the question was, well, okay, what if you have maybe some tall yellow bars over here and some tall yellow bars way out here? Wouldn't your Gaussian distribution not be a very good fit? So the more technical answer to this is that the cross-entropy method does converge. It's actually, oddly enough, it's a global optimization method under some unreasonable assumptions about the number of samples. And what's going to happen is that if you actually do have this bimodal thing, unless your function is perfectly balanced, like you literally have the same value on both sides and you get really unlucky and land right on that value, which basically never happens, the Gaussian will be just a little taller on one side than the other, and then you'll generate more samples on the taller side, so then it'll become even taller there. So this method actually does a pretty decent job of breaking ties. Sometimes arbitrarily, if you have too few samples, it might not pick the right mode if one of the modes is actually a little better, but it happens to have fewer samples on it. But with enough samples, it's a global optimization algorithm. Okay, and if you want to learn more about these types of optimization methods and you want some fancier stuff, if cross-entropy method is not fancy enough yet, you can look up things like CMAES, which is sort of like cross-entropy method with a little bit of momentum. So cross-entropy method basically discards all the information about the old samples each time, so once you refit this P of A, nothing about the old P of A or the old samples is actually retained. CMAES is kind of like a momentum version of it, so it sort of keeps track of which way it's been going, and it almost looks like kind of gradient-like in that sense. Okay, so we can use these, we can use this stuff to actually choose actions. We can use it to optimize for action sequences that achieve high reward. What's the upside? Well, these methods are very fast if they're parallelized. So they all involve evaluating the objective value on a batch of action sequences, which if your model, maybe your model is not actually known, maybe your model is actually a neural network, then those, most neural network evaluation packages will be pretty good at handling that parallelism. So it's nice that you can evaluate multiple action sequences in parallel. They're extremely simple to implement. So the guess and check, the random shooting method, is something that you can code up in 5 minutes. Cross-entropy method you can code up in another 5 minutes after that. But what's the problem? Well, there's a pretty harsh dimensionality limit. So short horizons, they'll accomplish some tasks, but they won't accomplish other tasks. So if you remember, for example, in homework 1, you had some of these tasks that you were experimenting with, like the reacher, the walker, and so on, the humanoid. Well, probably for something like humanoid, a time horizon of like 5 or 10 is not really going to work very well because that guy needs to plan over where he's going to plant his feet in order to walk, and if the horizon is shorter than the length of one footstep, then that's maybe inadequate to really plan those behaviors effectively. And of course, this is only providing us with open loop planning so far, and as we discussed in the stochastic case, the open loop planning can be suboptimal. Okay. So I'm not going to tell you right now how to address those problems. Instead, what I'm going to do is I'm going to shift gears to a different type of planning problem, but we will come back to this open loop thing and the dimensionality limit in the second half of today's lecture. But for now, since we're talking about stochastic methods, I want to talk about another stochastic method that's very popular in the literature. It's especially popular for discrete actions. You can use this for continuous actions as well, but especially for discrete actions, it's very popular. And this is Monte Carlo tree search. So unlike the stochastic optimization methods that I discussed before, Monte Carlo tree search does actually make use of the temporal structure in the problem. So it's actually a search algorithm, but a highly randomized search algorithm. So let's say that you weren't paying attention to the first part of the lecture, and you just decided that you want to be able to play these Atari games, and you're willing to, hack into the emulator a little bit to get this game to reset to different states. So this isn't the model-free setting anymore. This is actually the model-based setting, which means that you're allowed to go back to a state you visited before and try a different action. And then I might ask you, well, how can you frame the problem of playing the Atari game as a search problem? Well, you could say it's a kind of a tree search because you start off in some state S1, and then there are, 2 possible actions you can take in that state. So maybe you'll try each of those actions. Whatever state results from taking A1 equals 0, you'll explore different actions here, you'll explore different actions here, and then eventually you'll search deep enough in the tree that you'll find an action sequence that actually wins at the game. So what's the problem with doing this? The way I described it just now.
It's got an exponential explosion.
it has an exponential explosion, right? So if you have two actions, they lead you to two different states. If you have a horizon of capital T, it's going to be 2 to the capital T state evaluations. So at some point, if you want to actually like win the game of sequest, the game of sequest takes quite a while. So naively expanding everything obviously wouldn't work. So of course, if you think back to your artificial intelligence class or something like that, if you took a class that discussed how to do search, there's of course many, many better ways of doing it. But we're going to do something probably that's maybe a little different than what you've learned before. If you learn about like A-star or breadth first search, we're going to do Monte Carlo tree search. And the idea in Monte Carlo tree search is that we're going to basically cut off our search at some depth, but at that depth we need to actually evaluate something about how good these states are. So if you surfaced the submarine, collected some oxygen, lowered it right where you're about to shoot the evil fish, and you started shooting the fish, but you haven't gotten the point yet for actually hitting it, you might think, oh, this is kind of a lousy state because I haven't gotten a point yet. But if you were just wait a couple more seconds, you would have gotten that point and realized that that state is actually great. So intuitively, what you want to do at the bottom here is you want to just see from those states, how will things turn out if you just kind of wait around and don't do anything particularly smart. So wait around and don't do something particularly smart is not really like a very general concept, but what you can do is you can say, well, let's just run some kind of policy from these states. It almost doesn't matter which one, because this policy isn't really trying to win the game, it's just trying to figure out how good is this state. So, and of course, you can be smart about it and you can choose some really clever policy, but even a really silly policy, like a completely random policy, will give you something. Like if the little torpedo is about to hit the fish and you're about to get the point, even if you like wiggle the submarine around randomly, you'll still get that point and you'll see that this state, the state where you're about to hit the fish, is a really good state. So the main idea behind Monte Carlo tree search is that we're going to expand our tree in a kind of an adaptive way to a limited depth, and then we get to the bottom, when we get to the leaves, instead of actually continuing the expansion, which would be exponentially expensive, we'll just run some random policy to get some guess at the value of that state. Okay, so we can search, obviously, all the subtrees, so we have to pick what we're going to explore first. So let's say that I've expanded this subtree and this subtree, and when I play out my random policy starting from the action A1 equals 0, that random policy gets a score of plus 10. I don't know what plus 10 means. I don't know if it's good or bad. I just know that it's plus 10. But when I play out the other side, I get plus 15. Okay, so now I get to expand one more node. Which node should I expand? Can somebody say which node I should expand? S2, yeah, well, they're both S2. Right or left? Right, yeah, right. Okay, yeah, it's plus 15. Of course you're going to go right. You want the points for hitting all the fish. So the intuition is that you want to expand the nodes with the best reward, right? Because those are the ones that seem the most promising, but you have to remember that these evaluations are quite stochastic. You're running a random policy, which might not be a very good policy at all. So you don't want to just always expand the node that seemed to be doing best. You want to also sometimes expand the nodes that weren't visited very much. So if I keep going here to the right and I keep getting plus 15, I'm thinking, okay, I'm pretty sure this thing is plus 15 now. But here I only tried it once and I got a plus 10. Maybe I just got unlucky. Maybe if I try it again, I'm going to get like a plus 100. So you want to expand the best node, but also prefer the ones that were visited rarely. So here's the pseudocode for the generic Monte Carlo tree search algorithm. Step one, so it's obviously a recursive algorithm. So you start at some node, and at the beginning you always start at the root. And step one, you're going to find a leaf of the current node using some kind of, we call this tree policy. It's not really a policy in the sense that it doesn't emit actions. It's just a policy for the algorithm. So it's going to use some procedure called tree policy to find the leaf of the current node that it wants to expand. And at the beginning, there's only one node, which is the root, which is the state that you start in. So the subscripts, by the way, the reason that I said they're both S2, this is referring to the time step, not to the state. So this is the state at time step 2. Okay, so you're going to find a leaf of the current node that you'd like to expand according to some criteria called tree policy. Then you're going to evaluate this leaf using the default policy. This one is actually a policy. This is your random policy that you're going to run to the end. And then you're going to update all the values in your tree between the node that you expanded and the root. So each of the nodes in your tree has some numerical value associated with it, and you'll update all of them. So, and then you repeat. So here's how that's going to play out. Then of course, once you're done, then you take the best action from the root, because that's the best action you found. So the way that it's going to play out is, well, okay, if you start at the root, there isn't really much more to do. Like, you have to take some action, and you might as well pick them at random or pick them systematically going from 0 to n. So just pick the actions because you don't know what's going on yet. So maybe you execute action 0 first, and then of course once you execute it, then you play out your default policy. And let's say that you play it out and you get a total value for this run of 10, and we're going to call that Q. So you get a value of 10. And you also need to store the number of times that you evaluated this node, because remember, we're going to try to go to the less visited nodes more often. So you store the number of times you've been here, which is 1. And there's a little bit of a point of confusion that sometimes arises with this. When I say you've been here n equals 1 times, I don't mean that you've been at this state. I mean that you've been at this point in the tree. The point in the tree is determined by which actions you took. The environment might be stochastic. So when you take action A1 equals 0 3 times, you might land in 3 different states, but it's still the same place in the tree. So the node in the tree is defined by which actions you took to get there, not which state you're in. And then, of course, since we don't know anything else about A1 equals 1, we'll just execute the other action 2, and we'll play that out as well, and we'll get some value Q equals 12, N equals 1. Right? So now it seems like this one is a little bit better. So the tree policy that is most commonly used with Monte Carlo tree search, the tree policy is the one that decides which leaf you're going to expand. So now that I've actually expanded 2 leaves, I have a non-trivial choice to make. So now I better define what that tree policy is for you guys. The tree policy that's most commonly used is the following. If you're currently sitting at a node that is not fully expanded, meaning that you haven't expanded all actions from that node, then choose a new action that you haven't expanded yet. And if you're sitting at a node that is fully expanded, like the root over here now, then you choose the child with the best score. And the score is something we have to define. The score is going to be a criteria based on Q and N. So the way that the step 1 in MCTS works is you're at some node, look at whether all the actions in that node have been expanded. If all the actions have not been expanded, then pick a new action. And if all the actions have been expanded, like they have here at the root, then pick one of the children based on the one that has the larger score. And then if you go to that child, and that child has all of its has some unexpanded actions, pick a new action. If that child has already expanded all the actions, then you recurse and you pick its child that has the largest score, and so on and so on. So remember, the intuition for the score is that we'd like to choose nodes with the highest value, but also go to nodes that haven't been visited very much recently. So maybe over here, right now both of these nodes have been visited the same number of times, so we'd like to go here on the right because they both have n equals 1, but the one on the right has a bigger score. So we'll go there and we'll expand a new action for that node. And maybe here we get Q equals 10 and n equals 1. So now, remember that we have the step 3, update all the values in the tree between the leaf that you expanded and the root. So now here we have Q equals 10, n equals 1. And over here, we're going to add n and Q to the total. So we have n equals 2 and Q equals 22. And of course, you can always find the average value at some node by dividing Q by n. So the average value over here now is 11. OK, so now we actually have a choice. We have 2 different values of n, 2 different values of Q. This one has a bigger average. This one has a lower visitation count. So a score that we could use, this is, it looks a little cryptic, but this is kind of one of the most common scores to use in Monte Carlo tree search. It's a score that effectively performs a trade-off between trying to maximize value and trying to go to states that haven't been visited very much. Sorry, try to go to nodes that haven't been visited very much. So the first term here, Q divided by n, this is just the average value of that node. So that makes perfect sense. Just take the q, divide by n. And the second term is a number that's going to get smaller and smaller the larger n is. So it's going to get smaller as n gets larger because at the top it has a natural log. Sorry, let me just clarify this. At the bottom it has an n, which means that if you've been to the node st many, many times, it'll be divided by a big number, so that'll get small. At the top it has the natural log of the parent. And the reason for that is that if you visited the parent many, many times, then you want to choose, obviously the children will all have higher visitations because you've been to the parent more often. So if you visited the parent like 1,000,000 times, but you've only been to the child once, that should be a bigger bonus than if you visited the parent only once and the child only once, right? So that's why you have the ratio of the log of the visitations for the parent divided by the number of times you visited the child. So it's kind of, you're trying to find the most neglected child of that parent. So if you do that, now depending on your choice of capital C, you could go either left or right, but for kind of a reasonable capital C, you'll probably say that, well, here the average is 11, here the average is 10, but here the n is 1, so probably I'm going to prioritize the fact that the left child is more neglected. I'll go there and expand an unexpanded action, and maybe now I'll get a q equals 12. So again, I propagate it up the tree, which means that I add this number to everything from here up until the root, and I end up with 22 and n equals 2. So now, when I start again at the root for the next round of MCTS, both of these children look the same. So I'll just pick one arbitrarily, and I'll expand an unexpanded action, and here I get a q equals 8 and n equals 1. So when I add that up, now, question? Now when I add that up, I have a q equals 30 and n equals 3, which means here the average is 10, here the average is 11, and this one is a lower count, so I'll definitely go here, expand that one, and so on and so on. So I'll repeat this procedure until I exhaust my computational budget, at which point I will choose the action that goes to the best place. Does anyone have any questions about MCTS? Yes, question back there.
So is the C there like a tuning parameter, something you tune based on?
Right, so the C is a tuning parameter, and it makes a lot of sense that you should have a tuning parameter here because these Qs, they're going to be on some scale that you don't know. So you take the Atari game, you multiply all the rewards by 100, you probably need to increase C as well. The question there?
What are the factors of 2 about, given that C is a tunable parameter?
I don't know. That's just the textbook score that everyone uses. I'm sure it has some rationale behind it. Theoretical analysis of MCTS is kind of a very thorny area because it's an algorithm that, to my knowledge, still doesn't actually have any coherent guarantees in the general case. But the place where this, for a little bit of background, the place where equations like this come from are typically, they kind of have their origins in the bandits literature. So for bandits, you can actually have provable regret guarantees on certain kinds of upper confidence bound selection rules, and that's where a lot of these things in MCTS come from. But in the world of MCTS, they typically lack those guarantees. Yes?
Is time discounting built into any part of this?
So if you want to do time discounting, the way that you would do that is you would integrate it into how you compute Q. So you can compute that however you want. In fact, this doesn't even assume that the whole thing is Markovian. For all it knows, maybe the reward depends on whether you land in like the same state that you started in or something. There's no assumption about Markovian rewards here. You would just plug this into your simulator and let the simulator spit back a number, whichever number you like. Any other questions? Yes?
Can you explain again how you update that Q value for each node?
Yeah, so the question is, how are the Q values at each node updated? Very, very simply. So each time you expand a new action, you get a number. And that number is what you got from the whole trajectory, the rewards of the whole trajectory. And n for that new node is always 1 because this is the first time you've expanded it. So at that new node, you always write down the total reward for that trajectory and 1 for n. And then you take these and you add them to all of the parents, all the way up to the root. You just take the Q that you got here and you add it to the Qs of everybody up to the root, and you take the n and you add it to everybody up until the root. And what that produces is that it produces a value of Q, which is the sum of all the rewards of all trajectories that have gone through this node, and a value of n, which is the number of times you've gone through this node. So that means that when you take that ratio, you always get the average reward.
If it's possible to add explorations to this, like if you're greedy.
Right. So the question is it possible to add some kind of exploration rule to MCTS? So this term, the term that says you should go to the neglected children, that is essentially an exploration rule. It's saying that if you haven't taken some action enough times, go there more often. And in fact, when we talk about exploration MDPs later on in the course, we'll see exploration heuristics very similar to this that can also be applied in the world of model-free reinforcement learning. Question back there?
How is the default policy determined? Because it seems like it could bias the states that you.
Yeah, so the question is, how is the default policy determined, and can it bias the search? The answer is that yes, it can definitely bias the search, and that's one of the big things that actually complicates the analysis of MCTS algorithms. The way that it's determined is up to you. But kind of classically, in MCTS, the default policy is actually a random policy, meaning one that selects all actions uniformly at random. There's no reason to expect this to be a good policy, with the detail that it does give you full support, which means that if a good thing can happen in the world, the good thing will happen with some non-zero probability. In general, there's no reason to expect it to be a good policy, and a very natural improvement to MCTS is to use a smarter policy, which you can do. But the textbook version of the algorithm works like this. Any other questions? All right. So some additional reading if you want to learn more about Monte Carlo tree search. This paper by Brown et al. Is a survey of MCTS methods with a nice kind of basic pseudocode summary of the algorithm and a few variants. So if you want to learn more about different variants of MCTS, you can check that out. If you want to see an example of a paper that used MCTS in a kind of a reinforcement learning setting, this is kind of a fun paper to look at by Guo et al. And what this paper does is it actually trains policies to play Atari games, but uses MCTS to supervise that policy. So MCTS devises a plan to play the game, and then a neural network policy is trained to imitate that plan using actually an algorithm that we already learned about called Dagger. So Dagger basically just asks for additional labels at the states that the policy visited, and the way that those labels are produced in this paper is not by asking a human, but actually by asking MCTS. So that's kind of a neat way to use MCTS and still get back a neural network policy that can play some video games. Okay, so now I'm going to take a 3-minute break, and when I come back, I'll talk about continuous control and trajectory optimization. So we'll be back at 10:58.
What's the rationale to use like a breadth first search here instead of depth first search? It's just because we care more about the recent action that can change the state?
Yeah, so the rationale is to get effective exploration. So the intuition there is that because the whole process is stochastic, you can't necessarily, in contrast to conventional graph search, you can't really assume here that when you've evaluated some node, you actually got an accurate evaluation of the real value of that node. So if each expansion only gives you a sample of its value, then it actually makes a lot of sense that you might want to revisit nodes multiple times and kind of go broader, because then you'll have a more reasonable estimate of its value.
But when we revisit the node, we don't really change the state of the node, do we? Do we change the state of the node?
So when you revisit so a node here refers to a node in a tree, which is not necessarily the same state. So if the transition dynamics of the MDP are stochastic, if you execute A1 equals 0 3 times, you might land in 3 different states, but we still call it the same node in the tree. So a node is just fully determined by which actions you took to get there. So it's actually a distribution over states.
Okay, so when you say we actually, for example, visit this node, we rerun from S1 and then
Exactly,
and then,
exactly, yeah. Okay, let's continue. So before the break, we talked about how we could optimize action sequences under known models with stochastic optimization using random shooting, cross-entry method, and also for discrete actions, we could use Monte Carlo tree search, which actually takes into account the temporal structure of the problem. In the second half of today's lecture, we're going to talk about continuous actions and states. And I'm going to actually switch to the kind of more common notation in optimal control. Don't be scared about that. So as we discussed in the beginning of the class, if you see S and A, S refers to state, A refers to action. If you see X and U, X refers to state and U refers to action, because X is a really nice letter to use for unknown variables, and U is the first letter of the word for control. So if you see this kind of equation with X's and U's, you can mentally substitute S's and A's, but we're going to go with this notation here, which is more common in optimal control. So we're going to talk about how we can optimize action sequences, U1 through UT, by using derivatives. So before we didn't have any derivatives, now we'll put derivatives into play. So the original problem I started off with in today's lecture was that you want to minimize some total cost, subject to a constraint that says that your next state is equal to the dynamics evaluated at your previous state in action. And that's the same as maximizing your reward, of course. Since the constraint is an equality constraint, we can also equivalently write down this problem by just substituting in the definition for xt. So since xt is equal to f of xt minus 1 comma ut minus 1, you can substitute that in. So you have c of x1 u1, c of f of x of u1, x1 u1 comma u2, plus so on, so on, so on, and so forth. It takes a very long time to write out fully, which is why I have a bunch of dots in there. But it's an unconstrained optimization problem. It's an unconstrained optimization problem over your open loop plan, U1 through U capital T. So if we want to use derivatives, it's kind of the usual story with differentiable functions: differentiate via backpropagation and optimize. So compute the derivative of the subjective with respect to your variables, which are U1 through UT, and then optimize the whole thing by using some kind of gradient-based optimization method. Now, which derivatives do you need? Well, you have only two types of functions in there. You have C's and F's, so you need the derivatives of C's and F's with respect to their arguments. So you need to know df dx, df du, dc dx, and dc du. And if you have access to these things, then just by applying the chain rule gratuitously, you can compute the derivative of this whole objective with respect to your actions, and then you can take a step in the direction of that derivative. Now, in practice, if you simply use first-order gradient ascent on this kind of objective, you'll have some problems. And the reason that you'll have those problems is that if you look at, for example, this last term, if you imagine what its derivative will look like when you apply the chain rule, it's basically going to have df du multiplied many, many, many times for different time steps. And this df du, it's some kind of matrix. And if that matrix has eigenvalues greater than 1, then multiplying it together many, many times is going to give you a really gigantic number. And if it has eigenvalues less than 1, then multiplying it many, many times is going to give you a really, really tiny number. So first-order derivatives, relying on them too much here, can actually be some bad news. You can essentially get very ill-conditioned gradients, which will result in very ill-conditioned optimization problems. So in practice, if you want to actually use gradient-based methods to optimize problems of this sort, it really helps to use something that looks like a second-order method or like a 1.5th order method, something that uses some second-order information. So what we're going to cover in the last part of today's lecture is actually a very popular class of higher-order methods for these kind of trajectory optimization problems called iterative LQR. And I'm going to cover it for these kind of trajectory optimization problems, but you can imagine applying it to other kind of settings too, basically anything where you have this sort of sequential structure. So before we get into iterative LQR, I do want to say a few things about terminology, because this is some terminology that you might hear a few times, for example, if you work on robotics problems or optimal control problems. And I just want to mention it just so that you know what it means. So sometimes you'll hear somebody say, oh, I'm using a shooting method, or I'm using a collocation method. What that means is the following. A shooting method is a method that optimizes over actions, meaning that it performs a substitution to substitute in the constraint into the objective to get an unconstrained optimization problem. So this is the type of problem that a shooting method optimizes. And the reason you call it a shooting method is because these actions give rise to a sequence of states, but the way that you actually kind of pretend that the world works is you pick some actions, you shove them through your simulator, and you get back the sequence of states. So as you change the actions, kind of the whole trajectory wiggles around a little bit. So if I'm changing this first action, the whole thing is gonna wiggle. So it's sort of like I'm picking these U's, I'm shooting it out through my simulator and seeing what comes out. In contrast to this, you could actually solve the original constrained optimization problem, including both the U and the X as variables. So you can actually optimize over the states and the actions, and then keep track of these constraints. Which might seem kind of needlessly complex, because then you have both states and actions as your variables, but it can result in better behaved optimization problems, because now, instead of this whole trajectory wiggling as soon as you change the first action, the trajectory can move in more local ways. So if you change the states around a little bit, just part of the trajectory will change. And then usually the way that you do it is you would actually do some kind of relaxation and gradually enforce this constraint. Okay, but we're going to talk about shooting methods, which are methods that optimize over the actions and treat the states as sort of a deterministic consequence of those actions. And we're going to start with a simplified setting, which is the setting where the dynamics are linear and the cost is quadratic. And this is referred to as LQR, or linear quadratic regulator. I'm going to bring things back to more general nonlinear systems later, but I'll start with the LQR case because it's easier to derive, and then the math for the nonlinear setting will be very similar. So this is our problem. So it's a shooting method, which means that we've substituted the constraint into the objective, and we have this unconstrained objective. And when we say that our dynamics are linear, what that means is that f of xt comma ut is just some matrix capital Ft times the vector that you get by concatenating the state and action, plus some constant vector. So this is a linear dynamics. And the cost is quadratic, which means that it consists of a quadratic term, which is some matrix multiplied on the left side by xt ut transpose and on the right side by xt ut, plus some vector lowercase c multiplied by xt ut, and in general you can also add a constant to it, but adding the constant term of course doesn't change the optimum, so we typically ignore the constant term. So quadratic cost, linear dynamics. Linear, quadratic. Yes?
So how can you calculate the cost?
You mean where do you get these matrices? We'll actually discuss that later when we talk about the nonlinear setting. In the linear setting, we would typically assume that we're just given this matrix and this vector as part of the problem definition. All right. So now in this linear quadratic setting, we can actually calculate the optimal actions using a dynamic programming procedure that begins at the last time step and then progresses backwards through time. So at the last time step, our cost depends on two things. It depends on U capital T, it depends on the last action, and it also depends on X capital T. So there's only one term at the end, it's this last cost. UT is just an optimization variable, and XT is something really complicated that depends on all the other optimization variables. So what we're going to do in the LQR algorithm is we're going to treat this X capital T as an unknown, but we'll first solve for U capital T in terms of X capital T, and then we'll recurse backwards through time to remove that dependence on this unknown variable. So first we'll solve for UT in terms of XT. So how do we do this? Well, at the very last time step, there's only one cost term that depends on UT, which means that the Q function, which is now the Q function is actually the cost to go rather than the reward to go, just has this one term, the cost term, and some constants that we don't care about. We're going to use a little bit of fancy notation to break up this cost matrix into a piece that depends on state and a piece that depends on action. So the cost we assume that the cost matrix is always symmetric, and when you see me write C subscript xt, that's just the top left quadrant of the cost matrix that multiplies the states. If you see me write C subscript ut, that means it's the lower right portion of the cost matrix that multiplies the action. And then of course I have these cross terms, xt ut and ut xt. And similarly, we can decompose the cost vector into an upper portion that multiplies the state and a lower portion that multiplies the action. So now what I can do is I can compute the gradient of the Q function with respect to the action. It's a quadratic function, so if I want to find the optimum with respect to u, I have to set the derivative to 0 and then solve for u. So if I calculate the derivative of this with respect to u, it's actually pretty straightforward to do. You have one derivative term from the end. This term is just linear, so the derivative from the end is just the portion of ct that multiplies ut, which is c subscript ut. And then I have two terms from the quadratic part. I have one term from the cross term, which is basically xt transpose cxt ut, or ut transpose cut xt xt. But since the matrix is symmetric, and there's a 1/2 in front, I can just treat those terms as the same, just remove the 1/2. So the derivative of that is just cut xt times xt. And then I have the term that comes from this part, ut transpose cut ut. It's multiplied by 1/2 in front, so I take its derivative and I just get this part. Okay, so that's my derivative. I'm going to set this to 0, and I'm going to solve for ut, which is just a little bit of simple algebra. I throw this term over to the right-hand side, and then I multiply both sides by c ut inverse. And that gets me this equation for the last action. So it's just a little bit of linear algebra. The optimum for a quadratic, it's just given by this equation. Now this equation depends on xt, which as I mentioned is unknown at this point. But we're going to recurse and we're going to solve for it later. For simplicity of notation, I can write ut as being equal to some matrix times xt plus some vector. And of course, the matrix part comes from here. The vector part comes from multiplying this by this thing. So this is the equation for capital K, and this is the equation for lowercase k. So now I have an equation for the last action ut in terms of the last state xt. Okay, does anyone have any questions about this derivation? There are a bunch of symbols and a bunch of linear algebra, but the actual idea is actually very straightforward. You just compute the derivative, set it to 0, and solve for u. Okay, so now we have these things. These are the facts that we've determined from the last step. And now we want to do the second to last step, the time step capital T minus 1. So at the at the last step, our Q function was just the last cost. At the second to last step, this is not going to be quite this simple. At the second to last step, we're going to need to take care of the effect of the u subscript t minus 1 on the last cost and the second to last cost. So what we can do is we can use our equation for ut over here in terms of xt to eliminate ut from the optimization, and that'll actually get us the value function. The value function here at the last time step is the cost that we'll get if we land in the last state and then act optimally. Act optimally means execute this action. The way that we get that, very simple, we just substitute this equation for ut inside of our cost. And that's exactly what we're doing here. So here, it's just the equation for our cost at the last time step with xt and with ut being substituted for by this equation. And now this is only dependent on xt. Ut doesn't even appear there anymore. And now what I'm going to do next, which is I'm going to write out a really scary, gigantic equation. I'm just going to simplify this. And I realize that it sounds ironic when I say simplify, and instead I get an alphabet soup of symbols. But the purpose of simplifying this is just to get rid of some of this vector notation. So all I've done here is I've just written out this product in terms of the parts of C, the CXX, the CUU, and so on. And I've simplified this to write it out as a sum of two terms, X transpose C and this part transpose C. It's a huge alphabet soup. You don't have to worry about what's in that alphabet soup. What you should notice is that that alphabet soup consists of only two types of terms. Well, three types, actually. It has quadratic terms, linear terms, and constant terms. Constant terms we don't care about. And then we can collect all the quadratic terms and collect all the linear terms and write out the value function as just another quadratic function, but now only in X. And this capital VT collects all the matrix value terms, and the lowercase vt collects all the vector value terms. And if you want to know what they are, here they are written out, but it's just a bunch of linear algebra in addition. So we've collected all the quadratic terms, collected all the linear terms, and now we have a nice clean quadratic function that is only a function of x capital T that has eliminated u capital T. So now, if we want to solve for the previous time step u t minus 1, we can do so in terms of xt minus 1 by leveraging our value function, because our value function tells us the influence that x capital T has on the cost. So ut minus 1 affects xt, and the way that it affects it is through the dynamics, right? So x capital T is equal to our linear dynamics times the vector of xt minus 1 and ut minus 1 plus the vector lowercase ft minus 1. That's just the definition of our linear dynamics. The q function at time step t minus 1 is given by the sum of the cost function plus the value at the next time step. So this bit is the same as before, but this bit now this is a new bit that we have to consider. And our value function, as we saw in the previous slide, is itself a quadratic function xt. So now we're going to do another substitution. We're going to look at this line. This gives us xt in terms of xt minus 1 and ut minus 1, and we'll just substitute that in there. So when we substitute that in there, the equation for vxt becomes a bit more complicated, but all I've really done here is I just replaced all the xt's with this part. So now I get a bunch of scary terms, but all those terms are still linear and quadratic. And just like before, I can collect all the linear and the quadratic terms, add in these quadratic terms and these linear terms, and get back an equation for my q function. So I have quadratic terms, linear terms, and there's maybe some constants at the end, which I discard as usual. So now what I'm going to do is after I collect all the quadratic terms and all the linear terms, I can re-express my q function at time step t minus 1 as having a quadratic term qt minus 1 and a linear term lowercase qt minus 1. And again, if you want to know what those terms are, here I have them written out for you. So the quadratic term is just the quadratic part of the cost plus the quadratic part of the value function multiplied on either side by the dynamics matrix. And the linear term is the linear term of the cost plus this funny thing that has the linear term in the dynamics and the quadratic term in the value, and then this last term. So those are the q function, quadratic and linear terms. And then just like before, just like I did at the last time step, I'm going to take the derivative of this thing with respect to ut minus 1, set that derivative to 0, and then do a bit of linear algebra to solve for the corresponding action. And of course, just like before, ut minus 1 is going to be a linear function of xt minus 1 plus some constant vector, and the matrix and the vector actually look pretty much exactly the same as they did before, except that now instead of c's I have q's everywhere, and that's it. So now I have the base case, I have the case for t minus 1, and I can do the same thing at t minus 2, t minus 3, and so on. Does anyone have any questions about this part? Okay. So, crazy linear algebra aside, the structure of the algorithm is actually pretty straightforward. You start at the last time step, capital T, and you recurse backwards through time. So you go capital T, t minus 1, t minus 2, etc. And at every step, you're going to compute the quadratic and the linear part of your q function, which will express your q function as a quadratic function of the current state in action. You're going to solve for the action that minimizes q, which will give you a term that is linear in x and a constant term. Then you will substitute that equation for u into your q function, and that'll get you the value function. And then the value function is what you carry over to the previous time step. And then you just repeat this until you hit time step equals 1. So as you go backwards in time, what you're doing is at every time step, you're computing your action as some function of the state at that time step. So maybe you have 100 time steps. At the end, you compute u100 is equal to this thing. All the way back, u50 is equal to this thing. And eventually, you work your way all the way back to the beginning. And at the very first time step, you express your first action u1 as k1 times x1 plus little k1. And now, you're actually ready to solve for the full plan. Because even though you don't know the state at most of the time steps, you do know the state at the beginning. The state at the beginning is the only thing that you do know. So you know x1, which means that now that you know x1, you can actually zip up this whole thing all the way forward and solve for all the actions. So then all you do is a forward recursion. So for time step 1 through capital T, you evaluate the action. And of course, at time step 1, you know x1, so this is easy to evaluate. And then you evaluate the next state by using your known dynamics. So at time step 1, you evaluate u1, then you figure out x2, and then you can repeat, because now that you know x2, you can figure out u2. And then you do this all the way to the front, and you get a full sequence of actions. And these Q functions and value functions, they are in fact honest to goodness Q functions and cost and value functions, with the only difference being that now, since you're minimizing a cost, the Q function is the total cost that you'll get if you take U from state X and then act optimally, and the value function is the total cost that you'll get if you start from state xt and act optimally. So now these are things you're trying to minimize rather than maximize. A quick note about stochastic dynamics. So far we've derived all of this for deterministic linear systems. For stochastic systems, your dynamics, of course, are not deterministic anymore. So you have to pick some distribution, p of xt plus 1 given xt ut. Now, if you just pick some arbitrary distribution, you're going to get a really, really difficult problem. But a very common and very simple choice for stochastic dynamics in continuous control is to use Gaussian dynamics. So that basically amounts to saying, well, I kind of know how my system works, but all the stuff that I don't know about, I'm just going to model it as Gaussian noise, a zero mean Gaussian noise. So you say, well, I kind of know the laws of physics plus some noise. So if you have a Gaussian dynamical system, meaning that the distribution over xt plus 1 is normal, it's a normal distribution with mean given by linear dynamics and some fixed covariance, you can actually show that the optimal closed loop policy is important. It's closed loop policy. Now, the optimal closed loop policy is actually given by the same exact relationship that we derived in LQR with no change to the algorithm whatsoever, regardless of what this covariance is. So if you have, but it has to be a constant covariance. So if you have a constant covariance, meaning it doesn't depend on the state or the action, then the optimal solution, the optimal closed loop solution for these stochastic dynamics is to just employ the same control law that we derived in LQR. This is because Gaussians are basically symmetric. So if you make a mistake to the left or a mistake to the right, you respond in the same way. So checking this is left as an exercise. So if you want to do this, you can deal with the alphabet soup of algebra at home. But as a hint, the way that you do this is by exploiting the fact that expectations of quadratic functions under Gaussians have a closed form solution. So you can actually evaluate the expected cost under Gaussian dynamics, compute all the same derivatives that I did in the LQR algorithm, and come back with a solution. And you'll find the solution is actually to take actions according to this control law. And of course, the initial state is also no longer deterministic, but just like with the dynamics, we assume that the initial state distribution is also Gaussian. That's kind of neat, because what we set out to do was to solve for the optimal open loop sequence of actions. But in the process of solving for that optimal open loop sequence of actions, we actually got this linear control law that turns out to also be the optimal closed loop control law for stochastic systems, provided that those systems are linear Gaussian. Okay, so that's a little primer on the optimal control. And then the last thing that I want to do is, so that's the closed loop stochastic case. The last thing I want to do is bring this back to the nonlinear setting, right? Because linear systems are, sometimes you do actually get linear systems, but in general we might have nonlinear systems, and we'd like to have an algorithm to optimize action sequences for nonlinear systems. So in the nonlinear case, we can actually build on this LQR algorithm that I discussed and derive an iterative version of it called iterative LQR, which is also sometimes called differential dynamic programming, or DDP. There's actually a small technical difference between differential dynamic programming and iterative LQR, which I'll mention at the end, but people sometimes use them as synonyms. Okay, so the assumption in the linear quadratic case was that your dynamics are linear and your cost is quadratic. So if you have a nonlinear system with a cost that is not quadratic, perhaps what you can do is you can approximate that nonlinear system locally as a linear quadratic system. So maybe what you can do is you can compute a Taylor expansion of your dynamics and a Taylor expansion of your cost function. And we want linear dynamics and quadratic cost, so we will have a first-order Taylor expansion of the dynamics and a second-order Taylor expansion of the cost. So here I've just written out a Taylor expansion of f around x hat and u hat. And people sometimes refer to x hat and u hat, x hat 1, u hat 1, x hat 2, et cetera, as the nominal trajectory. So the trajectory around which you perform the Taylor expansion, the nominal trajectory. So I've expanded this around x hat and u hat, and I have a linear dynamics, where the linear term is given by the derivative of the dynamics. And I have a quadratic cost, where the quadratic term is the Hessian and the linear term is the gradient. And now what I can do is I can redefine my dynamics and cost to get rid of these minus terms, to just be linear and quadratic in terms of a different variable, in terms of delta x and delta u, where delta x and delta u are just x minus x hat and u minus u hat. So now we got back to our familiar form that we had in LQR. Everything is nicely linear and quadratic. We just have different variables for x and u that have these nominal terms subtracted from them. So now we can run our regular LQR algorithm with these dynamics f bar and c bar, using delta x and delta u as the state in action. So the iterative LQR algorithm basically works as following. Until we converge, we're going to repeat the following steps. Compute the first derivative of the dynamics around the current nominal trajectory. Initially, you initialize a nominal trajectory made by setting all your actions to 0 and evaluating the corresponding states. You evaluate the first and second derivative of the cost to get the linear and quadratic term of the cost. And then you just run LQR. You run LQR using delta x and delta u as your state in action, and using these things to build your dynamics and cost function. And then you run your forward pass, but you run the forward pass with the actual nonlinear dynamics. So the forward pass is going to actually evaluate the real f of xt ut instead of the linearized version to give you a real physically consistent trajectory. And that's important because you want to make sure that your trajectory is actually a trajectory that can happen in nature. So you're going to run the forward pass, and of course when you run the forward pass you need to add back in this u hat term because you subtracted it up here. So you're going to use the same control law that you compute in LQR, but now in here it's xt minus x hat t, which is the definition of delta x, and here you add in u hat t because you subtracted it up here. And then you're going to update x hat and u hat based on the states and actions that you visited. So you just take whatever states and actions you had when you ran that forward pass, and those become the new x hat and u hat. So locally linearize, locally quadrasize, optimize for the best trajectory, evaluate what it would actually do in the real nonlinear system, update, and then repeat the whole thing. So this is an iterative procedure that will gradually optimize your trajectory. Now, why does this work? Why is this a good idea? Well, it works because it's actually doing something that's extremely similar to Newton's method. So hopefully many of you remember Newton's method, but as a quick refresher, Newton's method does the following until convergence. You're at some point x, you evaluate the gradient, you evaluate the Hessian, and then you compute a new x, which is the arg min of this quadratic approximation to your function. That's what Newton's method does. Iterative LQR is an approximation to Newton's method that's making use of the temporal structure in the problem. So it's also building a kind of a pseudo-Hessian, it's building the full gradient, and then using that it computes a better trajectory. So iterative LQR is the same idea, locally approximate a complex nonlinear function via its Taylor expansion. So it's an approximation of Newton's method for solving that original unconstrained optimization problem. Now, it's not actually exactly Newton's method, because Newton's method uses the full Hessian. You can actually get an algorithm that is exactly equivalent to Newton's method and still has this dynamic programming structure. But in order to do that, you have to also include the second derivatives of the dynamics. So remember, we took first derivative of the dynamics, second derivative of the cost. If you want to get full Newton's method, you have to include the second derivative of the dynamics, which becomes this ugly term because now it's a tensor and you have this tensor contraction and so on. It's a little messy, but you can implement it. I wouldn't actually recommend it because for many of the dynamical systems that you'll deal with, cost functions are usually simple, but dynamics functions are usually complicated. So if you have a complicated simulator like Mujoko, for example, well, first derivatives of the dynamics are kind of okay, second derivatives might get really huge. So oftentimes, it's actually a good idea simply to omit these terms just because they make things more stable. In practice, the iterative LQR can in fact be shown to converge. It just doesn't converge as fast as full Newton's method, but when you have very unstable second derivatives, it might still be preferred. So the method that does include the full second order terms for the dynamics is referred to as differential dynamic programming, or DDP. Okay, so there is one more detail about Newton's method that I want to mention, and iterative LQR by extension. So if you were to actually do this argmin in Newton's method, this wouldn't be a very good idea. Does anyone know why, if you have a complicated nonlinear function?
The edge has to be positive.
The edge has to be positive definite. That's part of the reason, yes. There's another reason. So let me just walk through this quickly. If you have a complicated nonlinear function like this one, Newton's method is going to approximate it with a quadratic. And if you do the full argmin, you're actually going all the way to the bottom of this quadratic. Now that can actually overshoot because the real function, of course, is not quadratic, and the further you go, the more you'll deviate from the true function. So what you want to do in reality, if you're using Newton's method, is do some kind of backtracking line search. You want to go in the direction of the optimum, but not all the way to the optimum. You might want to backtrack a little bit until you actually get to a good point on the real function that you're optimizing, not on this quadratic proxy. And you can do the same exact thing in iterative LQR. In iterative LQR, the place where you put the line search is actually the forward pass, because the forward pass is what's evaluating the real function, the real nonlinear function. So all you have to do in the forward pass is multiply this little k term by some constant alpha. And you're going to start with alpha equals 1 and gradually decrease it. When alpha gets all the way back to 0, this term is 0, which means that on the first time step you execute action u1, because obviously on the first time step these two match. And if you execute the same action on the first time step, then on the second time step the states will match again, which means that you'll execute the same action again. So at alpha equals 1, you just get back the same exact trajectory where you started. So alpha smoothly interpolates between the place where you started and the optimal trajectory under the quadratic approximation. So that's how you put in a line search. Okay, additional readings, so these will be in the lecture slides on the website. And the last thing that I want to do before we conclude today's lecture is I want to show you a little video. You know, we talk a lot, this class is mainly a machine learning class, it's about reinforcement learning. But optimal control is actually a very powerful technique, and I want to show you a video that shows some really interesting behaviors that are produced by using this iterative LQR procedure. It's actually using it in a model predictive control loop, which means that every single time step it replans the actions using iterative LQR. So here's the video. This is from a paper by Yuval Tasta, Tom Ayres, and Emma Todorov. And here they're controlling a wide range of different dynamical systems, actually in MuJoCo, using iterative LQR. So here they have this little hopper guy. They apply some forces to perturb the hopper. They apply some force to perturb the humanoid, and the iterative LQR is controlling them to keep them standing. So here's the simplest system that they work with. This is called the Acrobot. Its goal is to swing up. So it's only actuated here at the elbow, and it's trying to swing up to be upright. And here the controller, without any learning, without any training in advance, figures out how to perform this task, and then they turn off the control, it swings around freely, and then they turn it back on, and it immediately figures out how to recover, just with optimization.
What does the blue line mean?
The blue line is just showing the planned path from iterative LQR for one link in the robot. So now they're going to push it with some wind, and it tries to stay upright. Here's a more complex robot. This is a swimming snake, and exactly the same method, and they're trying to get the swimming snake to go to the green dot while avoiding the red dot. And without any additional learning in advance, it actually just figures out a swimming gait just from running that optimization procedure through a known dynamics model. And of course, this is all interactive, which makes it a lot of fun to play with. Here is the hopper. The hopper is something that I think some of you guys might have tried in homework 1. Their hopper is going to be tortured a little bit. They're going to push their hopper with a little 3D mouse. Here, this is just passive. It's not being controlled at all. They're just showing off their 3D mouse. But now, when it turns orange, they're going to turn on the controller, which is going to try to stand, and immediately springs into action. And then when they perturb it, it's going to try to remain standing. Now, oftentimes in reality, you don't actually know exactly the true dynamics model, but you might have a dynamics model that's close to the true one. So what they're going to show in a second, I believe, is they're going to actually change the dynamics model, but not tell the algorithm about it. So that's coming up shortly. So here, they made the hopper half as heavy, but LQR still thinks that it has the original mass. So now it's trying to plan for a system that's much heavier than it really is. But you can see that because it's a closed-loop controller, it still figures out more or less how to stay upright, just not nearly as effectively as if it had the true model. So you can handle some amount of model error in this regard. And this is very important for us because we're going to talk about model-based RL in the future, where we learn the model, which will always be somewhat imperfect. And of course, they want to show it off on a higher dimensional system like this humanoid, and they're going to try to get the humanoid to stand up in the face of adversity. All right, so pretty complicated behaviors, just emerging through optimization. All right, well, that's everything. I'll see you guys next week when we'll talk about model-based RL, and remember to get your project proposals done.
You say I think methodology research, you say